Hello students, this is your Professor Omelianchuk, and today we're going to be talking about logical form, right? And we're going to be talking about how to understand and perceive logical form through the methods of abstraction, and then define it so that other people can see it as well using the methods of recursivity. Okay, it sounds pretty fancy, but it's actually quite simple. And a nice little example to get us started here will be these two arguments. Okay, so the one on the left, let's pay attention to that, says if Tiger will not do the homework in this class, Tiger will get an F. And that is definitely true per the syllabus that I have put together, right? Premise 2, which I don't think is going to be true of anyone in this class, is that Tiger will not do the homework. Okay, Tiger will not do the homework in this class. I don't think that's true in this class. I have hope for you all. But supposing it is true, it follows then logically that Tiger will get an F, okay? So when I say that the conclusion follows, what I mean is if these two premises are true, then this one has to be true, okay? Now that's not the case over here in this argument. Now you'll notice that the first premise is exactly the same as the one over here. Okay, so I won't rehearse that one, but now look at premise 2 that says Tiger will get an F. So therefore, Tiger will not do the homework. Okay, that does not logically follow. If these two premises are true, this one doesn't have to be true, right? This one actually can be false, right? Because we all know that if you don't show up to the midterm and the final, suppose you skip those days, then you'll get an F, right? So that's the issue here, all right? That's what's going on. Okay, and the way we kind of express that simply is that the truth of the premises is not sufficient to guarantee the truth of the conclusion. Okay, we need something more, right? True premises is just not going to do it for us. What we need is something to guarantee the truth of the conclusion. Okay, so we're going to need true premises and a good form, right? I talked about this a little bit already, about what deductive reasoning requires, right? That requires the argument to have good form, and we distinguish that from the other kinds of reasoning that there are, right? Non-deductive reasoning, okay? That's where you can have, premises that are true, but they don't necessarily guarantee the truth of the conclusion, but they do make the conclusion to be probably true, or likely to be true, right? It gives some credence to the conclusion, but not absolute certainty, right? Whereas in deductive reasoning, the premises, along with the good form of the argument, do guarantee the truth of the conclusion, okay? To just illustrate this some more, right? Think about this. This comes out of the book, right? This little story. Okay, suppose you're on a jury, you're trying to decide whether or not the defendant stole some jewelry, okay? So in most of our lives, we're doing non-deductive reasoning. Okay, we don't have the sort of mind that can get in contact with reality in such a way that it reveals the absolute truth. It's just not the kind of mind we have. Okay, in some cases we can do that in pure theory and mathematics and logic, right? Which is what we're going to be studying. But on a jury, okay, you're probably going to be reasoning like this. All right, so here's a premise. If the defendant did not commit the crime, then there's a good explanation for why he didn't do it. Okay, and so here's one. He's a good citizen, he hates jewelry, and he was 100 miles away at the time of the robbery. Okay, that's a pretty good explanation for why he didn't do it. And so therefore, we can be reasonably certain that he didn't do it. Now, can we be absolutely certain? Well, absolutely not, right? Because the conclusions the conclusion here in 3 does not have to be true if the premises are true. Okay, so maybe the prosecutor could tell us a little story, and he could highlight this word "good citizen" and say, well, what does that mean? Right? In a capitalist society, maybe that's true. A good citizen wouldn't steal anything. But in a Marxist society, well, maybe this guy had a interpretation of class warfare, and he was on behalf of the proletariat taking on the bourgeois, and so his citizenship required him to not only hate jewelry, because that's the sign of bourgeois class, but to get rid of it, to strip it from the bourgeois and redistribute the wealth from it to other people. Okay, so he has a motive. Okay, now how do you make sense of the 100 miles away thing? Well, he could have hired somebody to do it, right? He uses the proceeds from his other robberies, let's say, to finance more robberies. Okay, so that's a yarn we could tell, and hey, if you believe that story, you might not think that he didn't do it. You might actually think that he did. Okay, so you could turn this around into a deductive argument. All right, and you could say, okay, well, if the defendant is an upstanding citizen, hates jewelry, and was 100 miles away at the time of the robbery, then the defendant did not commit the crime. Hey, guess what? He's all three of those, therefore he didn't commit the crime. So in this argument, the form guarantees the conclusion if 1 and 2 are true, but of course, right, we just told a story for why you might not think 1 is true. Okay, so the whole point of this little rehearsal here was to kind of get you to see the difference between the different types of reasoning and how it might not affect the outcome of what you believe at all. Okay, because basically the same problems come up in each argument, right? It's just that the type of reasoning is relating you and your premises to the conclusion in different ways, right? And so this class is about deductive reasoning and working towards conclusions that are guaranteed, because that is a very powerful form of reasoning. It actually shows up a lot in our programming languages and our computers and that kind of stuff. And so it's worth pursuing this kind of logic just to get a handle on how it is that we can reason in a way that is that can give you absolute 100% certainty, so long as the premises are true. Okay? All right, so when we're detecting form, we like to think abstractly, right? That's the way we do it, okay? And so an example here from mathematics, which you'll see this immediately. What is the characteristic feature of this set of numbers? We have 2, 4, 6, 8, 10, and so on. Obviously, they are all even numbers. All right, but what does it mean to be an even number? Well, another thing you can notice about the numbers in the set is that they're all whole numbers. Okay, we don't have any decimal points anywhere, no fractions, right? They are integers. And then what does it really mean to say that they are even? Okay, what does that really mean? And the answer to that question is that they're all multiples of 2. Right, so you could formally spell it out like this. For any integer n, where n is a placeholder for any integer that we might come up with, if n is multiplied by 2, then n is even. Right, so you can substitute any integer you like for n. Okay, it could be 1, 3, 5, or 47. Multiply it by 2, and you get an even number. So a technical definition of even, it might go like this, okay? I'm not a mathematician, but you could say, all right, what we're gonna do is we're gonna get an alphabet of symbols on the table here, right? So we're not gonna use Roman numerals, we're gonna use our Arabic numerals and the letter X and Y. Oh, we'll get some parentheses, there you see those, and an equal sign, okay? So then we'll say that the expressions 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are permissible, and any sequence of them is permissible, right? So you could put them together in such a way, right? You could put like 1, 6, 7 together, all right? And then you could say that 2 is even, all right? And then let X and Y be any permissible expression, okay? Then X is even if X equals 2 times y. Now I haven't specified what times y means, all right, but whatever. That is a definition that's recursive, okay? Now what is characteristic about recursive definitions, right? Well, the pattern I want you to notice is how we kind of went from, getting our symbols on the table, specifying some simple ways we could put them together, and then more complex rules, all right? So the next slide will explain that more clearly. Right? You start out by specifying your collection of symbols, which is your alphabet. Then you go on to define your most basic terms or alphabetic expressions. And then you define more complex terms out of the basic ones. Right? So the basic point here is that by abstracting away excuse me. From the set of even numbers, we can identify the features they all have in common and then clearly define them in such a way that specifies instructions for identifying and producing even numbers in a way that never goes wrong. Okay? That's what a recursive definition does, right? It makes use of our abstracting process and then kind of collects the information that we get out of it and puts it into a step-by-step definition that you can follow that is infallible. Okay, that's what we can do with recursive definition, and we'll be seeing that sort of thing a lot in our logical languages, right? All right, so what's an argument? Let's talk about arguments a little bit. Arguments are collections of sentences. There's a special kind of sentence. Those are called assertions, right? Now, what's an assertion? Well, an assertion is a sentence that can be assigned a truth value, right? Now, a truth value just means a determination of it either being true, which is what T stands for, or false, which is what F stands for. Okay, so here's an assertion that has a truth value. This is a sentence that has a truth value. Okay, Atlanta is the capital of South Carolina. That sentence has a truth value. It's false, all right, and especially in our world. Okay, maybe in some other possible world it isn't. Okay, but in our world that's false. Okay, I say it has a truth value rather than it has truth value, because I've noticed that students tend to confuse the idea of the sentence being true with having truth value. It's as if truth is valuable, and so to have truth value means to be true. That's not what I mean. I say it has a truth value insofar as you can assign a T or an F to the sentence, all right? So that, just make sure that you understand what I mean by that, okay? All right, assertions, they can come in the form of fact or opinions, okay? So if you went through your Common Core American education, you learned about this distinction that facts are provable and opinions are not, okay? We ignore that distinction completely in this class, and you just have to understand, like, an opinion, sort of like the Beatles are the most overrated band ever, that can be true or false, okay? Just as, you know, it's a fact that Atlanta is not the capital of South Carolina, okay? It doesn't matter, right, whether it's an opinion or a fact, they can still be true or false, right? What you have to kind of distinguish assertions from are things like commands, questions, and emotive exclamations, right? Emotive exclamations are kind of funny, right? We can talk about those, right? They can be kind of ambiguous, all right? So here's something that I sometimes hear in our common day political discourse, that Donald Trump is an a-hole, all right? Now you could analyze that sentence and interpret it as an assertion, right? It could be true or false. Maybe there are some conditions, you know, necessary and sufficient conditions of a-holehood, right? That you know, that he satisfies. Okay, but more often than not, what people are saying is just Donald Trump, boo. Okay, they're giving him a thumbs down, and the word a-hole kind of does that work for us. But if you're interested in whether or not he does satisfy conditions of assholehood, you can actually check out this book by Aaron James, and his companion book that he wrote during the primary season of the 2016 election, Theory of Donald Trump, and you might be able to figure out that this is a true assertion here. And I don't mean this to be kind of like, you know, an anti-Trump kind of thing. It's actually a pretty interesting book. I recommend it just because this sort of politician is what we can expect in the future, because the way that our political discourse works today is that we kind of get these people who have to have a certain kind of stance in the world where they take every advantage available to themselves. They have an entrenched sense of entitlement, and then they're just immune to criticism, right? The whole kind of shaming campaigns that happen in social media that just don't really affect them, okay? And so that's just the sort of politician we can expect. It's a funny book. It's interesting. If you're interested in political theory, you might enjoy this, right? Philosophy can be kind of interesting in these sorts of ways. So anyway, this is a little detour just to kind of promote a more fun aspect of philosophy rather than just, logic chopping. Okay, anyway, detour over. Let's get into semantics, all right? Let's talk about that. Every argument is made up of an assertion, all right? Yes, that is true. And not just one assertion, but, you have multiple assertions, okay? So we have assertions that are true or false. Truth and falsity have to do with meaning, okay? So this is really important. Semantics has to do with meaning, all right? That's what semantics refers to, is meaning, things that involve meaning. And for us, truth and falsity is what we care about in this class, right? We also care about semantics of relations. All right, here's a relation. The cat is on the mat, right? So in order to determine the truth of that, right, well, you're gonna need a particular cat and a meaning of on. And then we could kind of take a look at this second premise here. The mat is on the porch. And so you can determine then that the cat is on the porch, right? This is a transitive kind of relation. Right? This is if x is on the y and as y is on the z, then x is on the z, right? Okay, so now we have to talk about syntax, and we need to distinguish that from semantics, right? Especially when it comes to arguments. We talked about how arguments are made up of assertions. Assertions are true or false. That's the semantic part of arguments. The syntax has to do with how we arrange things, okay? And so the way that arguments are arranged is that they have at least one premise, or they have a set of premises, that might be a better way of talking, and then exactly one conclusion. Okay, it doesn't matter if the premises say the same thing as the conclusion at all. Okay, it just doesn't matter at all. All right, so syntax has to do with arrangement. We care about how things get put together. All right, so here's an example, right? If my name is Adam, then my name is Adam. My name is Adam, therefore my name is Adam. Notice that the premise here in 2 says the same thing in the conclusion. No big deal. Okay, this is an argument. It's not a very interesting argument. It's made up of assertions, and it's arranged in a certain way. All right, let's take a look at this argument here. If I'm in Washington, D.C., then I'm in the U.S. Okay, I'm in the Washington, D.C., therefore I'm in the U.S. Okay, now with this kind of argument, you can see right away that if the first 2 premises are true, then the conclusion has to be true. All right, and we've seen this sort of argument form a bunch now. It keeps popping up. All right, so let's analyze it a bit. Let's take a look at what's going on. We see that the assertion in premise 2 is in this first part of premise 1. That's why it's highlighted in red. And then you see the green part in premise 1 is in the conclusion of 3. Okay? We also have this little if-then statement here going on in premise 1. And this type of format, this argument form, is a famous one that you should get to know right away. It's the form of modus ponens, right? Modus ponens is a form that looks like this. We have premise 1, it says if P then Q. Premise 2 says P, therefore Q. That is modus ponens. You could also have P be listed first and then the if P then Q listed second. That's also modus ponens, right? Modus ponens, just the idea is that if you have a conditional and then the conditional's antecedent given to you, then you can conclude that the conditional's consequent is true, right? And so we're going to capture this argument form in a little toy language that we'll play with here at the beginning of this semester called conditional logic, right? What is conditional logic? Well, it's made up of singular statements, right? It's also made up of if-then statements. And as I already mentioned on the previous slide, the if part is called the antecedent, and the then part is called the consequent. Okay, so we've kind of abstracted away from several different modus ponens style arguments, and we've detected these things. And now we can put them in a recursive definition for CL and come up with a little logical language. Here's how it looks. Okay, here's our alphabet. We got the brackets that we're going to use as the left and right parentheses, capital P, capital Q, and arrow. They constitute our alphabetic members, or members of our alphabet. And then alphabetic expressions that will be permissible. We're going to let P and Q be the permissible expressions of our language. Not the only ones, because we can take little p and little q. Right, this gets a little confusing, but I'll explain it to you. Little p and little q are like variables. They stand in for any permissible expression of our language. So if you remember back to the mathematical example about even, I was using x and y to stand in for any positive integer, right? P and q are going to stand in for any permissible expression I can create with this language. So then P arrow Q is also a permissible expression of our language. Also note that P and Q can be the same thing. Right? They don't have to be numerically distinct, right? We just use the P and Q just to stand in for any permissible expression of our language, okay? And then last but not least, nothing else is a permissible expression of our language. Permissible expressions of our language are called well-formed formulas. So here's some examples. P, Q, P arrow Q, P arrow Q arrow P, right? These follow the rules of the recursive definitions and therefore are called well-formed formulas. Sometimes they're called WFFs for short, like that, WFFs. These are not well-formed, are, because it's not in the alphabet. Same problem here. Here we're missing brackets, and you cannot put two sentence letters together like so. That one also is not well-formed. We're missing a consequent, okay? We can represent modus ponens in CL now. Here's premise 1, P arrow Q. Here's premise 2, P. And then, therefore, Q. Okay? Same thing here. P comes first, P arrow Q comes second, and then Q. All right? Okay, so there are some review questions here. I'll have you go through those on your own. You can find these slides on the course page and take a look at them and just try to verbally answer them. There's some practice questions here about whether or not things are assertions or not. I think that you can work through these by yourself. It's pretty simple. All right. The basic idea that I want you to get a handle on is that not every sentence is an assertion, and you needed to be able to distinguish really understand what assertions are. Okay. Here are some questions too that you can go over about like where the conclusion is in the practice problem, right? And so I'm actually going to end the lecture here at this point. That way you can get into the practice problems and take a look at things yourself. If you have questions, let me know, and I will talk to you later.